So the RK method that we are going to learn is the fourth order RK method. It is an improved version of Euler's method that we have learned previously in order to minimize the error. So it is the most accurate numerical method to solve ODE, and so it is actually derived from Euler's formula, but the function f is replaced by a weightage average of slope. If you want to learn how to derive this formula, you can go to the link here. But I'm going to be very straightforward here. This is the formula, and each k is represents its own value, and it is actually a function value of x at modified values of x and y. So let's learn how to use the formula using the same question with the previous example for Euler's method, which is y prime equal to y minus x squared. All right. Again, the first step is to sketch a table and then determine how many steps that we have to do. So for Euler example, we have to approximate y at x equal to 0.2. But for this example, we only approximate to the answer asks us to find the value of y at x equal to 0.1 with h equal to 0.1. So we only need one step to find our approximation value. Okay, so first thing first, you can substitute the value of y from the initial condition. So y equal to 0.5. Find the value of k. K1 is actually the function of x naught and y naught. So just substitute the value into the ODE and you get 0.5. And K2 is obtained using this formula. So it is the function of x and y at modified values, whereby the x is we add with h over 2, and y we also add with 1 over 2 times k times h. Okay. So this is the for K2, the x is 0 plus 0.1 over 2, and for y is 0.5 plus 1 over 2 times with K1. K1 that we have calculated previously, it's 0.5 times with the h, which is 0.1. So we have to find the value of function at x equal to 0.05 and y equal to 0.525. Substitute the value of x and y that you get here into the ODE to find the value of K2, which you will get 0.5225. And then similarly do the same for K3 and K4. Each of the Ks has its own formula. So this formula will be given to you during final exam and test. After you get the K1, K2, K3, and K4 values, you can use the final formula, the RK formula, which is this one, to find the value of y approximation, and you will get the value of 0.5522. All right, that is how to use the formulas to approximate the value of y at 0.1. Okay, this is another exercise for you to do. Please do on your own. Now let's learn about the accuracy versus computation cost. So the accuracy of a numerical method for approximating solutions can be improved by decreasing the step size. With this enhanced accuracy, unfortunately, the computation cost will increase. So let's see again let's see this part again. So let's go to Euler's method. And when I increase the step size here, now the step size is 3, increase it to 25, for example. So you can see the approximation is getting more accurate and more nearer to the actual values. So that is why previously I've said that reducing the value of step size will increase the accuracy, but unfortunately that will increase the computation cost because it will take more calculations for each steps, and the calculation will be complex, especially when the ODE is very complex. Okay. So in real application, we must find the balance between accuracy and computational efficiency. So we have to determine which step size is sufficient enough to obtain approximation and at an acceptable level of error. Usually in engineering, we accept any error that is less than 0.5, but we want the step size to give us the least computation cost, which means the higher step size is better than lower step size. For example, given the following data, an actual value of y at at x equal to 0.1 is 0.552244, we have to analyze which step size is sufficient to obtain approximation at error less than 0.5 with the least computation cost. So the data given here is the approximation value. This one is using RK method. And there are three different step size, 0.1, 0.05, and 0.025. So we have to find which step size can give us an acceptable value of approximation, but with least computation cost, which is we want to aim high step size, but sufficient to get accurate value. So how to get this value, this answer is to calculate the value of error. So let's start with the highest value of step size first, which is 0.1. Because our aim is to use higher step size in order to minimize calculation steps and computation cost. So the formula of error is approximate value minus actual value over actual times with 100. So just substitute the value here, given the actual value here is 0.552244 and the approximate value. Just look at the last row here, which is this is the final answer. All of these here values are only the steps. So for error calculation, this doesn't matter. Only the last part here is used for error calculation. So just minus approximate with actual and divide by the actual value, and you will get the value of error. For this case, for h equal to 0.1, the error is 0.00797, which is way less than 0.5, meaning that the step size of 0.1 is sufficient to obtain an accurate approximation. So you don't need more calculation step. You don't need to reduce step size, but you already get approximation at an acceptable level of error. All right, that is all for this lecture. Thank you very much.